Let's start. So we have been looking at pipeline ADCs, right? And in the last class, we kind of looked at how to implement this DAC and the residue amplifier. So let me copy this. And we saw that we can implement the two using a single MDAC circuit, and that essentially looks like this. It is basically a switch capacitor amplifier, wherein at the input side, the input switch capacitor branch is split into a total of 2 power B1 branches, where B1 is the resolution of the flash, of which the 2 power B1 minus 1 branches are controlled by the thermometric bits. And we saw the non-idealities that can arise and how to tackle them. And the major ones are these. First is the fact that the gain you have for the residue amplifier will not match the gain you have in the digital domain when you reconstruct. So what will happen if that is the case? The residue, which is the quantization noise from the previous stage, will not completely get cancelled. So how do we solve for this? We have, the issue is this gain here doesn't match this gain. So what is the solution? We do calibration and we do calibrate the digital gain. Okay. The other issue is amplifier nonlinearity. Once again, if the amplifier is nonlinear, you have to put the inverse nonlinear function again in the digital domain. Same holds good for DAC mismatch also. Even DAC mismatch we kind of calibrate in the digital domain, right? So looks like for anything and everything we have been saying that we'll do some digital calibration. So in this class we'll briefly look at some of the principles that are used in digital calibration. Okay. So again I will explain this with respect to this gain mismatch, but the same can be applied for any other non-ideality also. Excuse me, I'll erase this. So these are two-stage pipeline. So here let us say this is V1 and the second stage is V2. So how do we reconstruct the final output in terms of V1 and V2? V1 plus V2 by, let's say, the digital gain. This is analog gain. Okay, so let's say now we replace this ADC with this additive quantization model. So ideally at the output I should have the input plus what quantization noise? I'll have only the last stage quantization noise divided by the gain. But if the two gains are not matched, what will happen? I'll have Q1 into GA by GD. Is that okay? Cool. And as I mentioned, we have to correct for this by making these two gains equal, and the reasonable thing to do is correct it in the digital domain. So one brute force way to correct for it is what I mentioned briefly in the last class. So you can basically take this entire pipeline ADC. This is the entire pipeline ADC. Say you apply a pure sinusoidal signal at the input. At the output, if I look at the spectrum, I'll have one impulse corresponding to the sinusoid, and all the other bins will be due to the quantization noise. Right? And if the gains were equal, this quantization noise will be only the last stage quantization noise by the gain. If not, we'll have higher noise. So one thing to do is you can measure the quantization noise power and then go and change the gain here. But as you can see, this is intensive simply because to find the quantization noise power, you have to compute the spectrum. Fourier transform computation is going to be really intensive, right? Yeah, we have to have some digital circuitry here. See, here there should be a digital circuitry that should compute the Fourier transform, right? And then we have to go and tweak it, right? Finally you can't ship a computer with every ADC, right? Of course, if you have one single chip, you can do it in computer. But finally, if it has to be automated, it has to be included. So first of all, this sounds computationally very intensive. Secondly, in this case, I have assumed that I am feeding a pure sinusoid at the input. So which means I should have a provision to generate this pure sinusoid and feed it. Okay. And moreover, in general, the issue with these kinds of calibrations is that, see, here when I am calibrating this digital gain, I cannot use my ADC to digitize my actual signal, right? Because I am feeding a test signal here, which is some specific sinusoid. So I cannot be using the system in my final system. Okay, so I have to bring the ADC offline, calibrate it, and then put it back. And these kinds of calibrations, they are referred to as foreground calibration, wherein when you calibrate, the regular operation of ADC will be affected. And a better thing to do is what is called as background calibration, wherein you don't affect the normal operation of the ADC, but do the calibration in the background and correct for all non-idealities. So this is what is usually preferred. And I mean, this is better because in case there is change in the temperature or voltage, if you want to track any changes, this background calibration will take care. But in foreground, you can't do it. I mean, in practice, we can have a combination of two also. You can first do a foreground calibration, fix things, and then have background calibration to track for changes. So, I mean, today we look at a couple of techniques used in background calibration. And for that, let me copy this. So again, I'll take this example of gain calibration, but again, same thing can be extended for anything and everything. Cool. So one thing that can be done is this, or maybe let's see if you can come up with it. I will try to lead you to the solution. So let's say, I mean, forget that this is an ADC for now. Assume that we have some signal to which we are adding some noise. Okay. So if you look at it, the extent to which the analog gain and the digital gain are matched can be measured by looking at what portion of this signal appears at the output, right? That's what I have to do. But unfortunately, the signal that is added here is the quantization noise, which is not known to you a priori. This is an unknown signal, so it means there is no direct way for me to see how much of this is present at the output. So, can you suggest something to overcome this? I mean, forget that this is an ADC. This is a system where, along with my input, some unknown signal is getting added. And I know for a fact that the extent to which this analog gain and the digital gain are matched can be found by looking at what portion of the signal that is added here appears here. But the issue is the signal right now that is getting added here is an unknown signal. So there is no direct way for me to see if it is present at the output.
You can subtract this signal and
no, that's what I mean. In this process is what we can have non-idealities, right? The thing is, the signal is unknown. That is why I cannot say if it is present at the output or not. So what can be done? I mean, if the signal was known to you, we can do it. Right now I am adding only an unknown signal. So what can I do? Huh? I mean, nothing. Quantization noise, it's statistics is all approximate, right? See, simple, right? See, here I know that any signal I add here, that is going to appear here. Right now the only signal that is added is an unknown signal. We can add a known signal, right? So essentially you can add a known signal here, and usually the signal that is added is what is called pseudo-random noise or PN noise. Yeah, so have you guys heard of this pseudo-random noise? No? Okay. So I mean, this essentially it's essentially a digital data, like stream of ones and zeros. It sort of mimics a random thermal noise, random white noise. Okay, but it is not truly random because generating a truly random number is not trivial. It is a pseudo-random number. So what it means is, this is a periodic sequence. Let us say it has a period of L samples.
And it will be L minus, like
within those L samples, it will be random, and then it will keep repeating. So it's a kind of a pseudo-random number. Okay.
yes.
Right? And it turns out one of the reasons we use it is because, see, the signal that we add, that must be easy to generate. You shouldn't generate some complicated signal, and generating that should not be complicated. For generating this, it turns out you just need a bunch of flip-flops and some XOR gates. Okay. And second thing about this is that, being a random white noise, if I look at its power spectral density, how will it look like? It's going to be flat. So this is discrete time. So if the which means how will the autocorrelation look like? Autocorrelation is the inverse Fourier transform of this. So it's going to be a discrete time impulse like this. Basically, the sequence will be correlated with only itself. Even if you shift it to the left or right by one sample, there will be no correlation, right? So the second reason why we use this PN sequence is because of this property, which will be apparent soon. So now I have added this additional signal. So what will happen to the output now?
Plus PN.
That also will appear here. So PN times. Fine. So now my goal is to find out what fraction of this signal is present at the output. So how do you suggest we do that?
This.
Yeah, I mean, I of course have to use this.
Not that. Use this.
This
Property.
How do I do that? I mean, what operation I should do to find if
Inverse.
not inverse, like I mean this is general, right? Let us say I have two signals x1 x2. I want to find if a proportion of x2 is present in x1, or to put it in other words, I'm interested to find if there is any relation between x1 and x2. I'll do correlation, right? And how do I do correlation? If let's say I have two signals x1 x2, how do I do correlation?
Integral.
Huh? No, yes. Okay, I mean time shifted, but let us say, I mean I want to see just x1 and x2 are themselves correlated. So without time shifting I'll do it. So I'll just multiply it and take the average. I mean in discrete time it's basically similarly x1 of n times x2 of n, and then you take the average. I mean this is the same way how you find Fourier transform Fourier series, right? In there also you have a signal x of t. I know that the signal comprises of a whole bunch of sinusoids. So I want to find what is the fraction of this complex exponential present in x of t. I do correlation, I take this thing and take the average. So it's the same thing. I mean, so I can basically represent it as expected value of x1, x2, because loosely speaking expectation is taking the average. Here I am finding the average of this. So now at least it is clear what I should do. I should correlate this output sequence with my PN sequence. So let's see what happens. Let me copy this. Oops. So this is my output. Let me just put it in silent. Good. So this is the output. So let's say I multiply this by GD, because I don't want to divide. Multiplication is easier. So let's say I multiply everywhere by GD. So this is GD. This is this. So this becomes GD minus GA. This also becomes GD minus GA. Fine. So now I want to find the correlation of this guy with the PN sequence. So which means I am taking expected value of GD times. If I do that, I'll have GD times expected value of y times Pn. Let me write it quickly. Q2 times Pn plus I'll have GD minus GA into expected value of Q1 times Pn. So I know that this is a random noise, random signal. It has no correlation with my input. So what will happen to this? It will go to 0. This is now a quantization noise. This has no relation with the PN sequence generated. What about this guy? That will also go to 0. What about the last term? That will be 1. I mean, the sequence is correlated with itself. So if I take the signal correlated with itself, I will get 1. Cool. So which means now if I, let's say I call this correlation to be R. So R will tend to, let's say it will eventually tend to, what will be the value now? R is the correlation. I am calling this as correlation. Okay. What is the value? GD minus G. So from this what can I find?
How close it is.
Yeah, I mean upload, and then what do I do next?
Calibrate G.
Yeah, see, now I mean you see that we already have some analog gain GD. To get this output we used assume some value of GD, which could be the ideal value of 2 power B1 minus 1 or whatever. And when I do that and take the correlation, I get some value here. Ideally it should have been 0 if the gains were equal. If not, we'll get something. So from this I'll find what is GA, right? And once I know GA, I'll change my GD to be this GD, I'll say GD new. I'll update my estimate of GD, I'll say GD new will be this G. Okay. So this is one way in which you can do. But I mean in practice we don't do this in one shot because you want to.
How do you do this?
This is simple, right? This is just, I mean,
This is the
see PNC expectation is just average. You have to just add. You have put an adder, right? And remember, I mean, Pn is 0 or 1. Multiplication is trivial. You either take that number or don't take that number and average. So you just take the sum and do the average. This is trivial. You just need an adder. So this way it can do it, but instead of computing this autocorrelation once and finding the estimate of GD once, to get a better estimate we do it iteratively so that any changes will get tracked. Okay.
This is a continuous loop that you.
Yeah, we'll come to that. Yes, we'll have to do it continuously. How we'll do it is what we'll look now. Now I know that my autocorrelation is ideally should be this GD minus GA. So now let us say I plot the magnitude of autocorrelation versus the digital gain I use. How will it look like? At GA, what will happen to the value? It will be 0. And for values greater than GA, it will increase. For value less than GA, I am taking the magnitude. I mean, it will not go this, right? So it's a mod function, something like this. So you can think of it this way, right? So what I am doing is this. Ideally, what is the correlation I want? Ideally, you want it to be 0. Now I have some correlation R. So you can say that I am finding the difference between these guys, taking the magnitude of this, and I can define this to be as a separate function. I'll call it as a cost function. So I'm basically plotting this here. Okay. So now I have this. So if I give this plot, what will you say to be the optimal value of this GD? I just need to find the minimum of the function, right? And in principle, this cost function can be anything. You can have, it can be something like this, and you have to find the optimal value which gives the minimum of the function. So, and this you can do it different ways. One way to do it is this, or you can understand it like this. So let us say initially you had an estimate of GD which is lying somewhere here. At this point A, what can you say about the slope? At this point A, what can you, I mean, can you say anything about the slope?
Yeah.
Huh? It's finite, but I mean, is it greater than 0, less than 0? Greater than 0. And if your initial estimate of GD is here, to reach the optimal value, what should you do?
Go down.
You should decrease. So in this case, I should decrease GD.
Are you trying for gradient?
Yeah. So if at B, what happens? Opposite. So in this case, what should I do? I should increase GD. So this obviously gives you a straightforward way to update your estimate. So let us say I have GD of I. Now I have to refine my gain estimate, I plus 1. How do I do that?
Minus theta t, lambda t gradient you go.
I mean, if the slope is positive, I have to decrease it. If the slope is negative, I have to increase it. So it should be something like minus, yeah, some, let's say dc by dgd, and let's say it is some nu times this. And this nu is essentially, it will dictate how fast or how accurate you can do. If you choose a very small value of mu, it will from here you will take very long time, but eventually reach it. If you use a large value of mu, what will happen?
It will oscillate.
Yeah, it might do this. You might reach close enough to the optimal value, but you might keep oscillating between this. So this basically is speed accuracy trade-off, right? So in practice, you can use a large value of mu initially to reach the value closer, and then you reduce it so that you reach the exact value.
Machine learning.
Huh?
Almost like machine
Yeah, it's all same, right? This is basically called the gradient descent.
learning. Yeah.
It's all math. I mean, machine learning is new, right? It's all math and statistics. And essentially because you're using the gradient to estimate, right? That's all. And in practice, instead of taking the absolute value of the error for minimizing this, it turns out a better estimate is to look at the mean squared value of the error. Instead of looking at the absolute error, you try to minimize the power in the error, right? And if my cost function is defined like that, in this case, what is the cost function? I know what is R. So what is this? Yeah, square of that. So essentially GD minus GA whole square. Okay. So if I take the slope, what do I get? 2 times of GD minus GA. And GD minus GA is what? GD minus GA is R. So this is basically 2 times R. So if I use the mean squared error as the cost function, so this modifies to this GD of I minus mu times twice of this. So I think I can take it as mu by 2 here. So the 2 cancels. So here I have R. So this is the mean square error minimization. So this is called the least mean squares or LMS. So yeah, now you see that the update equation for your gain is pretty straightforward. You already have an estimate for your gain. You just find the correlation and then subtract it with a scaling factor that gives you a next estimate, and then you keep doing it iteratively. So this is the LMS update. I mean, we have derived it mathematically, but actually you can also understand it from a systems point of view in a slightly intuitive manner. Let's say this is what I have. Let me copy this. So here, let us say I try to find the transfer function GD of Z by R of Z. This is all discrete time sequences, right? I take the Z transform. What do I get?
Mu of 1 plus Z, 1 minus Z.
Yeah, or minus mu by. Is that okay? Here I have minus mu. This goes here, so this will be Z times GD. This will be 1 times GD. Minus mu by GD, Z minus 1. I mean, this is same as minus mu Z inverse by 1 minus Z inverse. So what operation is this? Z inverse by 1 minus Z inverse? Huh? I mean, it's an integrator, right?
Yeah.
Okay. So what happens here? I find the autocorrelation. I take the negative of the autocorrelation and then integrate it. Is that right? So if I were to model it, you can do it like this. So here is where I have the correlation R of I. So this minus will take care of the sign inversion here. So now I have the integrator here. So I'll just say this is the integrator. Right? And then I have a scaling factor mu, that's just trivial. I'll just mark it here. So this gives me, what does this give me? Huh? This gives me the digital gain GD. Now once I have the digital gain, what do I do? I mean, I need to close this loop, right?
This into that.
No,
This can use it as a calculator.
yeah,
New GD.
new GD, and what do we do next?
Then again calculate this RI.
That's what, to find RI, what do I need first? R is basically what?
The
Expected value of
PN and the output.
and the output. So I know the PN sequence. So what do I need to find? So what do I need to find here? First, once I get the GD, see, remember my output is V1 plus V2 by GD, or other way is GD times V1 plus V2. Either of them is fine. So the first step I have to do is I have to find V, and once I find V, I can find the autocorrelation, or sorry, not autocorrelation, I'll find the correlation by using the PN sequence, and then I can close this loop here. So as you see, this entire business is a negative feedback loop, right? And remember that in steady state, what do you want this correlation value to be equal to? You want this to tend to 0, which means this should tend to, no, the digital gain should tend to what value?
GA.
The analog gain GA, right? See, and remember that we are interested in steady state values, and these are all constants, right? They are DC signals. So loosely speaking, we are interested in the DC performance of the system. So this is a negative feedback loop. Can you comment? Let me push it down. Can you comment on the DC at the input of the integrator? No, in steady state, the DC at the input of the integrator, yeah,
0.
it should, why?
It should reach GD equal to G, right?
I mean, this is assuming we reach GD equal to G, right? Why do you say it will be 0?
Negative feedback loop.
So?
Error signal should be 0.
Yeah, I mean, why? I mean, let's say,
That is the
okay, let us say this is also negative feedback, right? Let us say have some K and then do the same thing and then enclose it like this. This is just an amplifier of, I mean, this is just a gain K. I am doing the same thing, finding V and finding the auto correlation and doing this. So here, will it be 0?
That is negative.
This is negative feedback, yeah. Okay, so let's try to contradict, right? Let us say this DC is not 0. Let us say it's some positive DC. If I say that the input to the integrator has a positive DC term, what can you say about the output? It will keep growing up and it will become infinite, right? But this is a negative feedback loop, and it is definitely stable because it has only one integrator. It is a first order system, and it's definitely stable. So which means the DC at the input cannot be a constant value. It has to be 0. I mean, this is same as the virtual ground principle, right? See, if you have an op-amp, ideal op-amp, this ideal op-amp has an infinite gain across all frequencies. So when you put it in negative feedback, you again say that the error signal here is 0. Whereas here I have an integrator. An integrator has infinite gain at what frequency? Only at DC it is infinite, right? Remember, integrator is like 1 by S. Only at S equal to 0 it has infinite gain. So since it has infinite gain only at DC, only the DC portion of the error will be 0. Is that okay? And in general this is true, right? If you have any working stable negative feedback system and if it has an integrator in that, the DC at the input of that integrator will be exactly 0 in steady state. Okay? So this is exactly 0 because we have this infinite gain here. That's the deal, right? If this was a finite amplifier, finite gain, this will not be the case. So now this becomes 0, so which means this should become, that should be 0, so this will tend to, I mean, so loosely speaking, all this optimization problems, all this optimization we are doing here, LMS or whatever, that is basically building a negative feedback loop, and it's exploiting the fact that if you have an integrator put in negative feedback loop, the error at the input of the integrator will be 0 in steady state. So this is a common basic principle that we will be using in many calibration mechanisms and in many circuits also. The idea is similar, right? You have some quantity, you want to make it equal to some other quantity. So you take the difference between the two, you get an error signal and give that error signal to an integrator and enclose the entire thing in negative feedback. And the negative feedback loop will enforce that the DC at the input of the integrator will be 0. So if the error signal is given as the input to the integrator, the error will go to 0. Okay. Cool. So now we sort of know how to calibrate this gain in this pipeline. So let me actually copy this. Just take this guy. Good. So now we know what to do. We'll first find the output. First we'll assume an initial gain GD. This could be your ideal value of 2 power b1 minus 1 or whatever. And then you find the autocorrelation, not the autocorrelation, sorry. You find the correlation R, which is the expected value of the PN sequence with the output, and then use the LMS update to keep refining your gain. So this way, you will continuously keep correcting for any variations, and the gain will track the analog gain. So this kind of calibration is referred to as correlation based calibration for obvious reasons. So now here couple of things to figure out. So remember that this is now an ADC. So let me replace it with an ADC. I want the PN sequence to be added to the output of this guy. So where can I inject the PN sequence?
After the ADC.
I wanted to add here, but how will I get it? It is not like I can go and just add it here, right? Because remember that this has to go here also. So here the signal must be the existing y plus q plus pn. So where can I add the pn sequence?
Between the junction and the ADC.
No, but that you cannot do, right? Yeah.
You can't add by doing away added, right? Without.
See, but if you do it, then your DAC will also have to change. See, remember you already have some let's say 2 power b1 minus 1 lines, thermometric bits. If you go and add a PN sequence, it is going to increase more.
Okay.
So which means your DAC has to become double the size, right? So what is the simplest thing you can do? You can do that, that's not a problem.
I do not understand. How do we insert PN? It means if I have
You'll add it.
4 bit 0, 1, 1, 1, how do you put this PN? If the PN is of my 4 length.
No, PN is just one bit data.
It's just continuously adding.
Yeah. Adding 0 or adding 1, that's all. The point I'm making is, see, you are going to this ADC output, let us say it has so many bits, right? Thermometric bits. Now a PN sequence is going to be 0 or 1.
But if it add 1, then it has to, for adding again another one, then it has to subtract 1.
No, nothing like that. You just keep adding it, right? That's all. The operation is simple. I have an ADC which was giving y plus q. On top of it, I am going to add this PN sequence which is 0 or 1. Every sample, I'll add a 0 or add an 1 depending on the sequence. So of course one thing is what he suggested, you can add directly to the ADC output, but that means that this can become extra 1 bit, right? The summation. So which means the DAC has to handle those many bits. So where else I can add? After DAC you can't add, right? That is not trivial. See, I want y plus q plus pn.
Before ADC.
One thing you can do is I can directly add at the input side, right? So now the input to the ADC is y plus pn, output will be y plus pn plus q.
How ADC will react to the digital?
It's a 0 or 1, right? So you convert this to some small voltage. You need to have a very small, 1 bit DAC. If it's 1, you add a small voltage V0. If it's 0, you don't add anything. But again, when you do that, you are adding an additional sequence at the input, which means you have to make sure that this entire guy is within the range. So the maximum amplitude for the input will reduce, right? So the other thing that is commonly done is this. See, let us say the ADC's characteristics, the first ADC's characteristics looks something like this. I'm just drawing some 3 levels. What I can do is, if the PN sequence is 0, I will say the comparator threshold I shift it like this. If the PN sequence is 1, I will put it like this. Now remember that this is fine because I have a redundancy in this gain here. I am not using the maximum value of gain here, which means even if I make an error in the comparator threshold, as long as within the tolerable range of plus or minus delta by 2, I will be fine. So I can basically change the comparator threshold here based on the PN sequence. If it is 0, I will choose some reference level for the comparator. If it is 0, I will choose some other reference level. So this will also add the same error, right? So this is something that is commonly done. So you will add the PN sequence to the comparator directly. And this act of adding this pseudo-random noise is often called dithering. So this is one of the commonly used techniques for calibration. But this is the basic principle, but there is one practical difficulty in doing this business, which is the following. So let us say, yeah. So here, right, this entire business is based on the assumption that when I correlate the sequence with the PN sequence, the first 3 terms tend to 0 and only this term exists. Now if you look at the second term, we are correlating quantization noise with the PN sequence. The quantization noise will have really small amplitude. So taking this guy to go to 0, it's fine. Similarly here, the same thing. Here we have quantization noise plus this itself will be close to 0. So it is okay. But the first term here, we are correlating the input directly with the PN sequence. Now the input is going to have the full scale amplitude, so it's going to be really large. So if this term has to tend to 0, you have to take this average for a really long time. Okay, only then this average will tend to 0. So the convergence will be really long. That is, only if you take this for long enough time, this entire thing will tend to 0, and only then this will hold good. So the time taken for this process to converge to the actual value, that will be really slow. On top of it, because this Y has really large amplitudes, that will sort of affect your final estimate of GD or GA here. So we'll have a large interference from this huge input signal. So in practice, if you do this, this has convergence issues. Okay. So because of this, what is done in practice is the following, or a lot of different things can be done. Even in the original paper, this was introduced. Finally, what they do is this. So let us say this is my first pipeline ADC. This is the 2-stage pipeline ADC. Let's say I give the positive input to this. Let us say I take identical ADC here, and let us say I give the negative input to this. So let us say this is giving data D1, this is giving D2. How will I get the final D out? D1 minus D2. So this I will do to get the final output. Okay. So now if I look at D1, it's going to have plus the input plus quantization noise from the second stage by, let us say, G1D. Similarly, if I look at D2, that is going to have minus this, and Q2 had different quantization noise, and let us say different gain. Fine.
Then G1 at A will be different.
Could be different, right? It's a different ADC. Need not be same, right? Nothing is identical. So this is G1D. Now let us say I dither this with a PN sequence PN1, and dither this guy with another PN sequence PN2, and note that these guys themselves will be uncorrelated. Okay. If I do that, here I'll have PN1 into 1 minus G1A by G1D. Pn2 into 1 minus G1 A hat by, right? So in the earlier case, the issue arised from the fact that the correlation of the PN sequence with the input was creating convergence issues. Okay, so I cannot directly take the PN sequence and correlate with the input. Okay, so now I have these signals. Can you suggest some other signal which can be used to correlate with the PN sequence so that the input signal is not present? I have to correlate my PN sequence with something related to the output signal. But directly if I correlate with the, let us say this D1, I have this input here. Okay. Similarly, if I take only this, I have minus this. So as he's suggesting, let us say I add the two. Let's say I get another signal, let's say D out common mode, which is, now what will the signal here be? I'll have something with Q2, something with Q1, something with Q2 hat, some term with Q1 hat, something with Pn1, and some term with Pn2. So now if I correlate this with Pn1, so this term will go to 0, these two will go to 0, 0, and this will also go to 0, and only the term with Pn1 will remain. So I'll basically get this guy alone, and from this I can get how should I change my G1. So what I do is this, I take the sum of these two, and then let us say I correlate with the first PN sequence, and then do the same LMS update. I will not show that at all, I will just directly show it. So I will directly go and change the digital gain here. Similarly, to get the gain G1D hat, what should I do? I will correlate with Pn2. If I correlate with Pn2, only this term will remain, and this term will give estimate of the gain for the bottom branch. So same thing will happen here. I will correlate with Pn2 and then go and change the gain G1D. So this is one way in which you can do this to avoid issues with convergence and interference from the signal. And this was what was originally proposed in the first paper. And in fact, this idea of using correlation for calibration was proposed only in the early 2000s. Okay. And
how did you do this dithering?
Sorry?
How did you do this dithering in the previous slide?
Okay, so here I want to add along with the input and the ideal quantization noise, something I should add, right? What I'm saying is, if this is the quantizer characteristics, if the PN sequence is 0, I'll change the comparator threshold to something. If the PN sequence is 1, I'll choose a different threshold for the comparator. So this way the error, this is simple, right? I have the comparator already. I'm going to give a reference here. I have, let us say, two reference voltages. So, right? If the PN sequence is 1, I'll do this. If the PN sequence is 0, I do this. That is one way.
But this cannot be done in SAR, right? I think SAR.
So also, I mean, SAR, the capacitors have to be changed accordingly. Or you can add a separate, like, it can be done. Okay, think about it. But this is nice because, see, you can add here directly. If you add it directly, the input amplitude will reduce. The other thing is what you suggested. I can add here, which means I have to change the DAC here. So the simplest way in which you can add the dither without affecting anything is adding to the comparator threshold. So as I was saying, this was proposed in the early 2000s, and till now this is one of the commonly used techniques. The basic principle is same. You dither the ADC by injecting a PN sequence and make sure that at the output you correlate it, and using the correlation information you do this correction. And of course you can't directly correlate with the output because it contains the input. You have to do some things around this, and what is that something you do that gives you different techniques. And probably I can show you one one of the papers that recently used this. Okay. Yeah, so this is one of the recently published JSSC papers in 2022. Again, it's a pipeline SAR. It has a lot of details, but I'll just show the calibration information. I think it was done here. Oops. Yeah. So as you see again, normally what we do is this, we add a dither so that the dither has a wide spectrum. Okay, and that is why if we try to directly correlate the output with the dither, we had issues, right? So what these people do is, instead of adding a dither which is completely white, they add a bandpass dither. You generate a dither so that its spectrum is not completely flat, it occupies only a small band. Okay. Now what they do is, the output I take the output and put it through a bandpass filter so that I select only this portion. If I do that, I will knock off the signal. So at the output of the bandpass filter, I will not contain the signal, I will contain the dither and the quantization noise. So now I can directly take this guy and do the correlation, right? And that's what they do. They take the bandpass filter output and directly correlate. This is the correlation, and this is basically the integrator, right? If you think about it, the transfer function is Z inverse by 1 minus Z inverse for this. So this is the same LMS update, but the deal is they avoid this issue of interference from the input signal by filtering out the input and making sure that the dither is not present in the same signal frequencies as your input. You can choose a small band of frequency where the input is not there, generate a dither present only in that band, and at the output you filter only that band so that the input is not present. So this is one thing.
You don't understand anything.
See, ideally you generate a dither which has a wide spectrum, right? So now if I do this, I can't directly take the output sequence and correlate with the PN sequence because the output contains the input. The sequence that I am correlating with the PN sequence contains the input also. So what is done is this, you generate a dither sequence which is bandpass like this. The dither is present only around a band of frequencies.
Okay, that was okay.
So now you take the output and put a bandpass filter, digital bandpass filter, easy to do.
Yes.
So now if I look at the output of the digital bandpass filter,
There will be no Y.
there will be no Y. Now the input sequence is not there. So this can be directly used to correlate, because now the entire dither is present, right? I mean earlier on,
This will be correlated with the type PN, right?
yeah, I mean see, when we I'll make sure that the bandpass filter allows the PN sequence, so the output of the bandpass filter will contain the entire PN sequence as it is. I mean here also you could have done this, you could have filtered this, but then at the output you'll have only a small portion of the dither. You would have lost the information about the dither. You need to make sure you don't lose the information of the dither sequence.
So now when I add it, won't be a wide band, but it will be just a
Narrow
small
band.
band.
Yeah. The deal is here also I could have done the bandpass filtering, but if I did this, I would have lost information of the dither in all these frequencies. So when I correlate it, it won't work. So the two sequences I correlate must contain the PN sequence. I mean, one is the PN sequence, and the output I correlate must contain the PN sequence completely and must not contain the input. That is done in this way. And again, there are multiple ways. I mean, if you think, you can also come up with new ways, right? There is, I think. I mean, that's why I like this, right? I mean, if you think about it, this ADC design, it is a beautiful amalgamation of analog circuit design, digital circuit design, and some signal processing, right? I mean, if it were left to a pure analog designer, that guy will just try to make this gain better and better, and beyond some point he will say, hey, this is the best I can do, this is the resolution I can get. But this is all possible because some circuit designer who knew basics of signal processing, did this entire thing and got this, right?